right, guys. Can you hear me on the mic? No? It's capturing. Everybody shut up. Very nice. Still nothing? Maybe I just need to turn it up. It won't let me. I have no control over the mic. It looks like it's working on the Panopto, which is where it more matters. Can anybody not hear me? Great. Welcome to possibly your second SI session. How many of you went to Hillary's session yesterday? Okay, a little less than half of you. For the rest of you, welcome to your first Biology 1610 SI session. We're going to start just by passing around a roll. Not rocket science. Put your name and A number on the side with the corresponding time that you go to class, 8:30 or 9:30. Nothing else, just name and A number. Okay. So I'm Parker. You guys probably recognize me from class. I did a little SI introduction, but if you're in the 8:30, you don't see me as often. I don't go to the 8:30 section. I go to the 9:30 section. So, yeah, I'm Parker. I'm from Bountiful. I grew up in Bountiful. Lived here in Logan for a few years now. I've been in SI. This is my third semester being in SI. Third time doing Biology 1610. Well, second time because Biology 1610 is only the fall semester, right? So I took this class 2 years ago. Obviously, I did well enough to be the SI for the class. So this is just me up here helping you guys understand what I did to do well in the class and just give you an extra review, right? I'm not going to teach you anything new. So if you ask a question and I don't know the answer to it, I'll just tell you I don't know, okay? I'll make a bigger fool out of myself trying to tell you an answer that I don't know, and then one of you calls me out because someone in here always knows more than me, or their smartphone is faster than me. I'll just tell you I don't know, and you'll have to find it out on your own, right? I'm not a professor, okay? I'm an undergrad student like the rest of you. If it's not pertinent to the class, if it's not going to be on the test, if it's not important enough that I want to take the time, I'll just tell you. You don't need to know that. It's not on the test, whatever. I feel like that's more fair to you guys than sitting here and going over and over and over stuff that isn't even going to be on the test. We'll waste our time, right? But that being said, ask any question, literally any question. And even if I tell you I don't know or it's not important, at least you know, A, that I'm dumb enough not to know it, or B, it doesn't matter, so don't waste your own time trying to study it, right? I took all the tests that you guys have taken. The test this year will not be identical to the test last year or the test before that or any test, but they are extremely similar every year. And I know what Dr. Mott and eventually what Dr. Pogorski like to test on. So I can say, don't worry about that too much, or hey, definitely focus on this. Those kinds of things, right? Yeah. I don't know what else. Any questions from anybody? Everybody just having a grand old time? All right. I like to start off with some jokes. They're usually, comics or memes or something like that. So one is to my doctor after getting laser eye surgery. So how do I shoot them? The other one is 2 carbons. He says, Susie, these past 2 years have been amazing, but recently I've just felt like I've been living a half-life. Come on, guys. Like we just talked about it in class. At least act like you think I'm funny, or I'll leave. I can't. I'd get fired. All right. So if you're not here for the Biology 1610 SI, you can stay or you can go. Doesn't matter to me. We still have like a bunch of seats left if you guys want to just pop in. I don't even know how many seats are in this room, but you're going to have to get cozy with strangers. Welcome to college. I also like to always start out with an interesting biology fact. I find biology fascinating. My major is human biology. I want to go to med school eventually, become an eye doctor, hence the the laser eye surgery joke. But yeah, I love biology, so I put up these interesting biology facts just to show you guys, like, there's cool stuff in biology. I know half-lives and carbon dating and all that stuff's not the most fascinating thing in the world for everyone, but I try to come up with stuff that I think is pretty cool. So there's a jellyfish called Turritopsis doornhii. It's an immortal jellyfish, lives off the coast of Japan. It's not immortal in the sense like it can never, ever, 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 ever die. It can be eaten, it could be, you know, crushed or blown up, you know, whatever. But it can't die of natural causes. It's immortal. If it gets sick, if it loses a limb, if something happens, some kind of natural disease, if it, you know, gets cancer or whatever, it just reverts back to a pupal state. So it's like goes back to being a baby, and then it just grows up again. And then when it gets really old or it gets bit by a shark or something, it just goes back. And its life cycle is literally a cycle. It just goes over and over and over. So they can live thousands of years. So I think that's pretty sweet. If you don't think that's cool, I don't actually care. All right, so I wanted to take a few minutes just to talk about what'll be the most important things for this semester, right? And also to kind of open it up to questions if you guys are worried about mastering biology, if you're worried about the test 2 weeks from now, whatever you want to talk about, right? So I just wanted to start off by telling you guys this is not an easy class, okay? If you took this thinking, I took AP biology in high school, or I like science, or I got straight A's in high school without really trying, I said all of those things too. And I did not do super well on the first test because I was a little bit cocky. I was like, well, you know, like I did well in high school and I like science and blah, blah, blah. I didn't do terrible on the first test, but I did not do nearly as well as I thought I would. And I went, oh crap, this is actually a lot harder than I anticipated, okay? So be ready for that. This is a hard class. Don't freak out, it's doable. Every single one of you in here has got this. Okay, vocab and concepts are going to be your best and worst friend, right? If you know the vocab and you understand the general concepts really, really well, you're going to do really, really well. If you aren't memorizing vocab, if you're struggling to grasp a certain concept, that's partly what we as SIs are here for, but that should also be a warning sign to you that you're not on track, right? If you don't understand what carbon dating is, you're not going to be able to answer a complex conceptual question about carbon dating. It's logical, but you don't think about it until somebody says it, right? And then the last tip I have is review, review, review. As Dr. Mott has said a bunch of times, we cover an insane amount of material in a single semester. If you hear it once in class and call it good, that is not going to be enough, I promise. You'll sit down on the test and you'll go, oh, I don't remember that at all. Or you'll go, oh, I thought I understood that concept because I heard it in class and went, yeah, that makes sense. Okay, review it all the time. Come to SI sessions. Come to all 4 if you want and can. I did. All 4 sessions every single week, and I went to a lot of the UTFs when I could. And it helped a ton because you get to hear it in class, then you get to hear it in Hillary's session, then you get to hear it in my session, then you get to hear it in Chase's session, and you'll get it. It's just repetition, right? Plus, Chase will present it in a different way, and he may cover things that I don't cover. And same with Hillary. She may present it in a way that makes more sense to you, or she may ramble on less than I obviously do. But come to all of the sessions, okay? And if you can, if you can't, I get it. But review as much as possible. All right, so my whole rant's over. We'll actually talk about biology now. It only took like 10 minutes, so nobody freak out on me. Does anybody have any pressing questions about biology or a specific topic that we're hoping to hear tonight or anything? Or am I just going to awkwardly stand up here and wait for someone to ask a question? Because I'll do it.
I had questions about the pH section.
Okay. I have a couple slides on it. Did you have like a specific question or you just want to hear it again?
Probably just hear it again.
Okay, yeah. Pretty much right at the end of my slides I have a couple with like a practice problem and we'll go over it again. Anybody else?
Are you going to go over C14 dating?
Fairly briefly. I think I have a practice problem on Halflives, if that's what you're looking for, just specifically carbon dating. I don't go over it a ton because it's not a massive concept, but I'll talk about it for a second. If you still have questions, talk to me after, look it up in the book, email one of us. But yeah, I'll talk about it for a second. Somebody else had a hand. Definitely have a couple slides on that. Do you have a specific question? Just want to hear it again? Okay. If you guys want, there's still 7 or 8 seats mixed throughout. If you want to sit on the floor, you do as you please.
Molecular shape, you're going to go over that?
Like those?
Yeah, the 3D.
I was hoping somebody would ask about that. I think I have a slide on it. I saw 0 test questions on it when I took the test, and I didn't review it in my sessions last year, and nobody came to me and said, why didn't you say anything about molecular shape? So as far as I know, it's a pattern. We don't really go over that, but I have a slide just so I can show you guys. Don't worry about this, okay? So if you're confused as to what I'm talking about, we'll get to the slide and I'll say, this wasn't on the test when I took it, and I'm pretty sure it wasn't on the test last year. Don't freak out about it. Okay, we're gonna dive in, but ask questions as we go along, right? This isn't a lecture. I'm not up here to talk at you. If nobody asks questions, I will just talk at you, and then we're all bored. So, I already did that. Real quick review of what emergent properties are. The actual definition is a property of a system that exists at one level of organization but does not exist at the levels below. The levels below. It should say at. Somebody want to put that into normal people words for me?
It's kind of like with a bike, right? How you can have the gears and stuff that you can put in, so the bike's all fitted.
Okay, yeah, so Dr. might use the example of a bike. I think he also used a car. Its individual pieces don't do anything, right? If you don't put the wheels and the chain and the handlebars and the pedals and all that together onto a bike, it's not going to do anything, right? So each piece builds to something, okay? What else, though? There's something else I'm also looking for, because that's definitely it, but there's another piece to it. Nobody wants to seem overeager and answer questions really fast. You can just sit in silence.
Okay, so all of the different levels of organization have different components in them, and that's kind of like the car, they all make it up. So without one of those, they can't exist. Or
Yes.
is that kind of like it?
Yeah. So what you're saying is it does not exist at the levels below, in simpler terms. So, for example, let's say, an organism. Anybody, quick definition of an organism? A living thing, right? Is a molecule considered a living thing? No. But if you put some organelles together and build a cell, is that a living thing? Okay, so levels below don't have the same qualifications, so they build on each other, okay? That's the whole idea of emergent properties. I wish this pen would let me skip so I don't have to walk back and forth. My feet are going to be sore by the end of the session because I'm an old man. Cell theory is just that all life is made of cells. Everybody should know that. New cells only come from existing cells, meaning you can't just snap your fingers and poof, make a puppy, right? It'd be sweet if you could, because they're like $900. But you have to get them from already existing cells. So a male dog and a female dog do what male dogs and female dogs do when they love each other very much, and you make a puppy, right? But they have to come from somewhere else. They don't just appear, right? And then you got 2 types, prokaryotic and eukaryotic. Which one exists more abundantly? Prokaryotic, right? It was kind of a confusing question in class. I don't remember exactly how the iClicker went, but it was a little bit all over the place because we think eukaryotic cells are bigger, right? We're eukaryotic. Whales are eukaryotic. All mammals and most animals that we think of are eukaryotic. So we think, yeah, there's more of them, but there are more prokaryotic cells in your body than your own cells. You're mostly made up of prokaryotic organisms. Well, we can get into a whole philosophical discussion, but there's more bacteria on your skin than me cells in my whole body. Okay, so there's so many more prokaryotic cells. Prokaryotic cells are about half to 1 micrometer long. Eukaryotic cells are 10 to 100 micrometers long, so they're 10 to 100 times bigger, right? Quite a bit bigger. They're still tiny, but relatively. All right, natural selection. Obviously on the slide it says individuals with adaptive traits leave more offspring. Somebody simplify that for me. What am I saying?
When an animal or an organism has an advantageous trait, such as like in the right picture, if the beetles are darker, they're more likely to survive. So over time, that's an advantageous trait to have, so it's more likely than dark beetles.
Okay, so it's some kind of advantage that helps them survive. The longer they survive, the more likely they are to reproduce and have more offspring, right? So they're considered more fit, right? The dark beetles live longer because they live on a dark substrate, dark ground. They get picked off by the bird less frequently, right? Because they blend in better. What could Dr. Mott ask on a test about natural selection? Somebody give me an example of a test type question about this.
I think it was on the Mastering Biology practice question, but it asked if every 50 years people over 6 feet tall were eliminated from a population, what would happen to the population?
Okay.
And the answer was the people would become shorter.
Okay, why?
Because the tall people are dead.
Yeah, you keep killing off tall people, they stop showing up. No. The more often you kill off tall people, the less frequently they get to reproduce and share their tall gene, so fewer tall people appear, right? So that's a test type question to say what would happen if you took a bunch of white beetles and black beetles and tossed them on some white sand, who would live longer? You know, just conceptual questions that help us see if you grasp the idea behind natural selection. Questions on natural selection? Evolution is not natural selection. They are related, but a lot of people think, oh yeah, that's what Darwin was talking about. Evolution is the idea that all life descends from a common ancestor, okay? This is key and fundamental to biology. Now, this is where I always put out a disclaimer. I'm not challenging anyone's religious beliefs. Believe what you believe about evolution religiously. But in this class, evolution is real. It's what happened. And you have to understand it and answer test questions appropriately. And then when you go home, you can decide whether or not you believe in evolution, okay? They have so many evidences for it, right? The cilia of a paramecium, which is just, it's a little microscopic organism. The cilia are like the little hairs on it, have the exact same structure as the cilia on the cilia in our windpipe, okay? The exact same structure. That's the odds that that's due to chance are insane. There's almost no way that we have the same exact cilia as paramecium for no reason. Unless you look at evolution and say, what if way back, millions of years ago, we started to split off from some kind of common ancestor. It doesn't mean we came from paramecium. Paramecium didn't come from us. But we split off from the same ancestor and evolved. And now we're very different from each other, but we share a single trait that links us all the way back, right? That's evolution. So when people say we're descended from monkeys, what they really mean is we had a common ancestor with monkeys at some point way back millions of years ago along the line, and we each kind of split off from them, right? Does that make sense? Again, believe what you believe, but answer test questions appropriately or you'll not get a good grade. Questions on evolution? I shouldn't jump ahead. There's still a bunch of seats if you guys want to jump in. If not, stand in the back. Do whatever you want. Life. 25 different chemical elements. An element is a substance that cannot be broken down by chemical reactions, okay? So name some elements for me. Just shout them out. Carbon.
Titanium.
What?
Titanium.
Titanium. Uranium. Oxygen. Hydrogen. Potassium. Okay. All of those are elements. It's that periodic table that you've seen in your elementary school classroom since you were 5 and never understood what it was. They can't be broken down, right? Hydrogen doesn't break down any further by chemical reactions, right? You can put them in a particle accelerator. You can break them down into quarks, and we can go further into that. But that's more like quantum physics stuff. We don't need to talk about it. What we do worry about is that 96% of the mass, the biomass, living things, is carbon, hydrogen, oxygen, and nitrogen. John. Okay? Just remember Chan. Oh, you can't really see it, can you? Can I dim the lights somehow? Probably not. I don't see anything. It says Chan up there for those of you who can't see it. Oh, there's a bunch of light switches here. I'm nervous, though. Oh, that's better. Yeah, so I would just know those 4 elements, carbon, hydrogen, oxygen, nitrogen, make up the vast majority of the biomass, at least on our planet. An atom is the smallest unit of an element, right? So an atom of carbon, an atom of hydrogen, like I said, cannot get any smaller. You can't get any smaller than an atom of hydrogen and have it still be hydrogen unless you break it up by non-chemical means, right? So atoms are uncharged, okay? Because it has the same numbers of protons and electrons. And if protons are positive and electrons are negative, then they cancel each other out, right? And when you have the same number, even if you have 200 and 200, they're still canceling each other out, right? When it's an ion, that's a different story. That's when you start seeing differing numbers of electrons and protons. So if protons does not equal electrons, it's an ion, right? So if you had 7 protons and 6 electrons, then it would have a slight positive charge because it has more protons, right? So it would be a positively charged nitrogen. Did I say 7? So nitrogen ion, right? Yeah. So an electron, a proton, and a neutron. That's usually how you'll see them. Obviously, these aren't 2-dimensional things. They're 3-dimensional, and we can't even necessarily draw them because the electrons can be at any given place at any time. So for our purposes, we draw them flat like that. Questions on atoms and ions?
Should we have carbon, hydrogen, oxygen, and nitrogen memorized for how many protons and electrons they have?
No. I'm going to say no on that one. When you take chemistry classes and things like that, you will memorize them just by how many times you do them. But for this class, no. Be able to tell how many protons or neutrons or electrons it has, like if you're given something like this, but don't memorize it. You got plenty of other things to memorize. Other questions? If you don't ask, I just move on. All right, so we already said protons have the positive charge, electrons have the negative charge, neutrons are neutral, so no charge. Now, atomic number is the number of protons. The atomic number is also the number of electrons, because again, they're equal in an uncharged atom. And then the number of protons determines what element it is. Okay, so 6 protons, always carbon. It cannot be anything else ever. If it has 6 protons, it is carbon. Okay, if it has 8 protons, it is oxygen. There's no ifs, ands, or buts. Okay? So let's talk about how to tell what something is. So you're given element X. There will appear a number here and a number here. This upper number is the mass number. That's protons plus neutrons, right? This lower number is just the atomic number, just the number of protons, right? So if I give you element X and I say 6 and 12, how many protons?
6.
How many neutrons? 6. How do you know that? It's 12 minus 6. How many electrons?
6.
How do you know that? This is number of protons. They're equal to each other, unless it were like some kind of charged element, but we won't do that kind of stuff in this class. As long as no plus or minus appears there, they're going to be electrons and protons are going to be the same number. Okay? Questions? I posted these slides online, so if you want to download anything from my slides, if you're like, ooh, this picture actually really helps, I'd like to have it for my own reference. If you just want to go through the slides, whatever, I posted them. You probably already all got the email that I made an announcement. I'm sure you love getting them, and I will never stop giving them to you because I love you. I like you as a friend. Isotopes. Okay. Anybody want to explain to me in their own words what an isotope is? You've already learned this in class, so you should know it.
It's an atom that has more neutrons than its counterparts, I guess.
That's semi-correct. Some isotopes have more neutrons. But give me the general definition.
Isn't it like technically like all of one element, but they can have different amounts of neutrons?
Yeah, so that's just a little bit more correct because it includes even the standard state element, right? But each of these is carbon, right? Because it's got 6 protons every time. But then your number of neutrons is what differs, okay? So there's carbon 12, has 6 and 6. Carbon 13, how many protons? 6. How many neutrons? 7, right? Because 13 minus 6 is 7. So it has 1 more neutron than carbon 12. And carbon 14, same thing, 8 neutrons. So it has 2 more than carbon 12. But each of them is carbon. Each of them can be found in nature. Carbon 12 is what you're going to find 99% of the time. Carbon 13 you find 1% of the time. And then carbon 14 you find such insanely minuscule amounts of it because pretty much the moment it becomes carbon 14, it kicks off a beta particle and becomes nitrogen 14, right? Picks up an extra proton there. So
why do the masses change? Like, why is that like a thing?
why are they getting extra neutrons?
Yeah.
Who knows, man? I don't know. I feel like I should. I've taken a lot of chemistry, and I've taken this class 3 times. No, it's not something we worry about too much in this class. If you want to learn more about it, do it. I think physics and chemistry are also awesome. I don't know what is causing them to pick up extra neutrons. Nobody knows. Somebody knows. Other questions? Taking it as a no. Practice question then for you about how to calculate half-lives. Okay? The half-life, so the amount of an element disappears to half of its original amount. So this is cesium-137, is 30 years approximately. I think it's like 29 point whatever. I didn't want to make you guys do that. Its half-life's 30 years. If you start with 1,000 grams of cesium-137, how much will you have after 90 years? Take 30 seconds. It's mostly mental math. You should be able to do some quick division here. Tell me how many grams will be left after 90 years. And E is already not the correct answer. You care because you want a good grade. Anybody got an answer for me? A? Anybody else think it's A? Put your hand up. Most of you. The rest of you suck? No. That's not appropriate. It is A. Tell me how you did that.
Well, there's 3 half-lives. If it's 30 years, there's 3 half-lives in 90 years. So you just divide 1,000 in half 3 times, which gives 125.
So 3 half-lives, because you saw that 90 over 30, not 3, is 3. So we're having 3 half-lives. And so you take 1,000, divide it 3 times, and you get 125 grams remaining. Correct? Is that how you did it in your head? Does anybody have a different way of doing it? There's not always one single way of doing math.
It's not divided by 3, it's divided in half 3 times.
Oh, I don't know what I'm doing. I don't even know what 1,000 divided by 3 would be. So it's not 1,000 over 3. Don't pay attention to me. It's 1,000. Now I gotta redo this whole thing. Thanks, dude. 1,000 divided by 2. I don't know how to. Would it be 1,000 divided by 2 divided by 3? I don't know how you write that. You guys know what I'm saying. You would divide it by 2 and then divide. So that's what, 500? And then you divide that by 2 is 250. And then you divide that by 2 is 125. So the key is you have divided it in half 3 times. Thanks for catching that. Other questions?
Are the questions about carbon dating, like, or half-lives this easy usually of math?
They're pretty mental math stuff, yeah. You won't see, like, I'll show you in a second.
So yesterday at Blue SI, we did one with carbon. Is that like the only half-life that we know?
That's the one with like 5,000 whatever. Well, the thing is, you don't have to like memorize any of them. You should just be able to know how to run this formula. So, yeah, so it'll pretty much follow this format. It'll ask you how much will you have after 90 years. If the half-life is 30 years, so just do 90 over 30. That's the number of half-lives. Then divide your amount in half the number of half-lives that you have. Does that make sense? And that way you can do it for any like I don't even know what cesium is, to be honest with you. I Googled it and just said like weird half-life, you know. And I don't know what cesium does. It's just the math of it, right?
So what do you do if it's not a whole number like that? Like if you had 92 divided by 30?
Still technically the same thing. It's the same procedure. You'd get a weird decimal. For this class, we won't do anything like that because he just wants to see that you know how to do it. So it'll be whole numbers. And it'll almost always be like divisible by 5 and stuff. It's pretty easy. He just wants to see that you know how to do it. You won't need a calculator. Yeah. Other questions? Did that answer your question? I don't want to just skate by it. All right, okay. No? Okay. So what you won't see is something like this. The half-life of radium-226 is 1,620 years. If the atmosphere contains 0.01%, what would be the percentage in a biological specimen that has been buried for 6,480 years? This requires a calculator, right? Because you have to take 6,480 divided by 1,620. That's the number of half-lives. I want to say 4, probably 4. Then you have to divide 0.01 in half 4 times. Does anybody have a calculator that happened to be doing it real quick? Huh? I actually don't remember off the top of my head. We got one person saying they think it's E. E. You did it on a calculator, or you're just a genius? Okay. He's just super smart. It's D. Or I formatted the slides wrong when they switched over. Did you?
Oh yeah, we divided it.
It's showing E on yours. So the format didn't switch over, right? For everyone watching on Panopto, it's 000625. Okay? You're not going to see something like this. I just wanted to show you guys. This is not something you're going to have to do, right? They're not going to be this crazy. They're going to be about this level, okay? If you're not comfortable doing this level, there's nothing wrong with that. Come talk to me, talk to Dr. Mott, email us, look it up in Mastering Bio. Do what you got to do, right? Don't just say, I don't know how to do it.
So you will not need to bring a calculator to any of the exams?
I believe no. I'm pretty certain you will not need to.
Can you?
It's not a bad idea because I think they'll let you, so why not? But if you don't have a calculator or your calculator dies or whatever, don't panic. There's pretty much no math except for like some quick stuff in your head. Plus you get scratch paper and pencil, so if you need to write stuff down real quick, you should be able to do this without a calculator. All right. Other questions on that before I jump on? How much time? Still got like 15 minutes. Electron orbitals. The first shell has 2. The second shell has 8. Full shell is considered inert. A partially full shell is considered reactive. Okay? So just know there's 2 here and there's 8 here. All right? When there's an empty space, that's when another element can share an electron or steal an electron or something like that, right? That's how bonding occurs. But if all 8 are present, it's not going to do anything with anyone else, right? It's like, I'm full, I'm good, I don't need to react with anyone. I got this, right? Okay, these are some vocab words that you really need to memorize, and you really need to understand well what they mean. So covalent bonds, electrons are shared between the atoms, right? So one of them doesn't take the electrons from another and run off with them. They just kind of share them between themselves, right? Covalent is shared. Ionic is the opposite. Electrons are gained or lost. That's how you get a charged ion, right? That's why it's called ionic bonding. That's where ions come from, right? Sodium and chloride are the most kind of common examples, right? Sodium and chloride come together. Chloride steals one of sodium's electrons and fills its shell and becomes negative. I should draw this out so you guys can actually see what I'm saying. So you got sodium and chloride. I want to say sodium has 2 electrons. Don't quote me on this. And chloride has 7. So it just takes this guy from sodium. Sodium becomes positive, right? Because its number of electrons went down. Why would a decrease in electrons make something positive? It has more protons than electrons now, right? So it's got a slight positive charge. Well, if this chloride just picked up an extra electron, what's going to happen to its charge? Obviously, negative. It's got more electrons than protons, and it's now a chloride ion. And that's actually how you get table salt. Cool stuff, right? Everybody's thrilled. All right, so not the most important, they're all important. Hydrogen and polar covalent bonding. This is when carbon and hydrogen, they attract electrons more weakly, right? They have carbon's not on here, but hydrogen and carbon attract electrons more weakly, right? You don't really need to go into why. It has to do with their electronegativity and all that, but hydrogen just doesn't pull on the electrons quite as strongly. Nitrogen and oxygen attract them more strongly. They pull the electrons a little bit more. So this is still a covalent bond, right? They're still sharing the electrons back and forth. Oxygen just gets them for more time, right? It has more custody, visitation rights, however you want to consider it in your head, however you got to make like a real life example out of it, right? Oxygen gets more time with the kiddos. Hydrogen doesn't. So hydrogen has a slight positive charge. It's not necessarily an ion in that sense. It just has a slight positive charge to it because the electrons spend a little bit less time with it. That's how we get hydrogen bonds, because this hydrogen has a slight positive charge to it, and this nitrogen has a slight negative. They can be attracted to each other. They don't necessarily have to bond with each other, but they're kind of like magnets. As they get closer together, they pull on each other, right? Because they have the opposite charge. And it can also happen if this nitrogen were an oxygen. And that's actually how you get hydrogen bonding. Hydrogen bonding is specifically this hydrogen to if this were an oxygen. That's how hydrogen bonding happens. Questions on bonds?
A lot of times the word hydrogen bonding and the polar covalent bonding are used like next to each other. Can you think of them like interchangeably as words, or are they two different bonds?
Hydrogen bonding, did you want to say something?
I was going to say, so if I'm not mistaken, hydrogen bonding is like like a type of polar covalent bonding?
Pretty much, yeah.
Okay.
So hydrogen bonding is a type of polar covalent bond that happens between a hydrogen and an oxygen. Polar covalent bonding in general is just when any slight negative charge and a slight positive charge attract each other without necessarily forming a covalent or an ionic bond. So yeah, hydrogen bonding is a type of polar covalent bonding. Make sense? Other questions?
So just for clarification, a hydrogen bond is only between hydrogen and oxygen, or are there other hydrogen bonds?
That's it. As far as I'm aware. Maybe I'm lying. Oh, maybe I am lying. Hydrogen bonds can also apparently occur with nitrogen. When we talk about them in this class, it's just with oxygen, because we look at like the special properties of water that we'll look at in a second. But yeah, a polar covalent bond is when it's got a charge to it. A hydrogen bond is when hydrogen specifically is involved. Other questions? So let's talk about the special properties of water. Because of hydrogen bonding, we get some interesting interactions going on with water, right? We get all kinds of actually really important properties out of water that life would not exist on this planet if hydrogen bonding didn't work the way that it works. So you don't need to know all the ins and outs of why hydrogen bonding does it, but it does these 5 things. It has cohesive properties. What that means is there's a little bit of surface tension on the top of water, right? Those polar covalent bonds, those hydrogen bonds, have just a little bit of a pull to them, right? So something really, really light like an insect can stretch its feet out on the water and not break through, okay? Because that polar covalent bond has just enough pull. If I were to put my hand on it, right, I'm a little bit too big for that, but something small can do it. Or water will stick to its, the idea is that water really is sticking to itself. So if you pour a glass full of water, it'll actually kind of brim over a little bit. You guys have seen that before, right? And then it kind of spills over. If you were to do that with like, I don't know, even something that's not pure water like soda won't do that, right? It'll get to the top and it'll just run. It doesn't kind of bubble up like that. Is anybody confused on what cohesive properties are? No? So it expands, becomes less dense as it freezes. It's actually one of the only substances that will do this. Everything else becomes more dense when it becomes a solid. That's kind of the definition of a solid, is it's more dense than its liquid form, right? If you were to, if you had liquid steel, right, and you let it cool down, it'll actually get a little bit smaller and denser, right? Because density is mass over volume, so if you decrease the volume without decreasing the mass, you've increased the density. If that went way over your head, anything but water basically gets smaller when it gets cooler, and that's how it becomes solid. Water, on the other hand, actually expands. Those hydrogen bonds kind of stick out in sort of a crystal shape, and water will, instead of condensing on itself as it freezes, it sticks out. That's why ice floats. So water is also one of the only substances that floats in itself. Okay, if you took a ball of steel and you dropped it into liquid steel, it goes straight to the bottom. But you take an ice cube and you drop it in some water and it floats on top. Who can tell me why that's so important?
Well, so then the lakes and stuff don't freeze clear to the bottom.
Yeah.
The ice doesn't fall down. But that happens because the hydrogen bonds don't slide past each other anymore, right? They become like a solid, not like a crystalline structure, but almost.
Yeah, they spread out
Yeah.
instead of condensing. So the water floats on top. Otherwise, Bear Lake would freeze, and then that top ice would sink, and then it would freeze again and sink and freeze again and sink and freeze again and sink, and then Bear Lake would just be solid ice. And I don't care how hot it gets in the summer in Bear Lake. I was just there over the weekend. It's not hot enough to melt an entire frozen lake. So all of the water on Earth would freeze solid, and pretty much everything would die. So if hydrogen bonds didn't do what they did, we wouldn't be here, right? Polarity makes it an excellent solvent. Who can explain to me what that means in regular terms?
Because water has partial negative charges on it, it's able to bind with other elements or whatever is in it. Pretty much it has a partial negative charge as well, and then because of the hydrogen bonding, it pulls it apart.
Exactly. So have you guys ever like made a pot of mac and cheese and then left it out for too long and the cheese gets all crusty on the pot, right? Or your roommate does it. Goodness knows my roommates did. And you can't really get it off, right? What do? You soak it. Okay, so you leave the pot in some water for a little bit. The water actually breaks down the cheese molecules. They're not, cheese isn't a molecule. You know what I'm talking about. It breaks down the cheese and makes it easier to scrub off the pot, right? Does that make sense? Somebody want to explain that to my roommates? They don't get it, no. So the idea is that water has a polarity opposite to the cheese, and that allows it to actually attract the cheese a little bit and break it down and pull it off the pot. Okay, so water is kind of considered the universal solvent. Most things will dissolve in water. High specific heat. What the heck does that mean?
It's hard to raise the temperature of water.
Okay.
Specific heat is the amount of energy required to make something warmer in temperature.
Yes. So water, there's actually a numerical value to this. I don't know it, you don't need to know it, but water has a specific numerical value to its specific heat. It's the amount of energy, probably in like kilojoules, required to raise probably like 1 square centimeter of water, 1 milliliter of water, I don't know, by 1 degree. Okay, that's the specific heat. And that applies to all elements. The specific heat of nitrogen is the amount of energy required to raise nitrogen by 1 degree, like a container of nitrogen by 1 degree. Okay? So it has a high specific heat. What does that mean? It takes a lot of energy to raise water 1 degree. Okay? That ties into high latent heat of vaporization. Okay, and this is actually the picture from class of a swamp cooler. What does high latent heat of vaporization mean then?
Essentially, because it's hard to warm up, it's hard to evaporate, it's hard to vaporize.
Yes. Did you have something? No? Just saying what's up? What's up? So if it has a high latent heat of vaporization, that means it takes a lot of energy to get it to change states from liquid to gas, right? It takes a lot of energy to evaporate water. Again, the whole mac and cheese thing, you guys know, it takes for freaking ever to boil a pot of water when you really want some mac and cheese, right? Especially if you have a crappy electric stove like mine and then it smokes everywhere and the firefighters get called and then they want to share mac and cheese and it's ridiculous. So it takes a lot of energy to turn water from liquid to gas. So that's how a swamp cooler works. How does a swamp cooler work? We talked about it in class. You don't have to be an engineer.
It's stuck in the air, and the water comes down, and it pulls it because of the cool water. The air loses some of its heat because the water absorbs it, right? And it goes down into your house or whatever.
Pretty much, yeah. So the hot air comes in and hits this pad full of water, which makes it kind of more humid air, right? It increases the humidity of the air, okay? Then the heat just from outdoors heats up the water rather than the air, and it actually, in that sense, it pulls hot water out of the air, which cools the air down. Then you get cold air pumped into your house. Okay, so this is also how misters work, right? Have you ever walked outside and they hang a bunch of misters up in the air, right? It makes the air cooler. You probably think just because water is cool, right? So it's nice. You get hit by the mist and you feel like it's cooler. Well, what's actually happening is the water is entering the air, getting heated up by the sun, and getting evaporated, right? And pulling the heat with it. And the air around you gets cooler. So the water doesn't even have to hit you, right? You could build a ring all the way around you with misters, and the mist could never actually touch you, and it would still be cooler, because just the air in general, the heat is being taken by the water. That's what that means. It's a very long, roundabout way of explaining it. Did that make sense? Nobody's acknowledging me. Thank you. Questions about special properties of water? Excellent. pH. Technically it's 550. I'm going to keep going because pH is important. Technically you're free to leave whenever you want. Technically you don't even have to be here. So if you got somewhere to go, do whatever you want. I'm going to keep talking about pH. It is a big deal. You're going to need to know how to do this. So pH is a measure of hydrogen ion concentration, okay? Remember that, remember that, remember that. pH is talking about hydrogen ions. How many hydrogen ions are in something, okay? So that's what this guy is, okay? We're looking at the hydrogen ions. An acid has more hydrogen ions, and a base has fewer hydrogen ions. That's what makes them acidic and basic. That's the basic definition of this, right? So pH is actually a logarithmic scale, okay? So a pH of 2 and a pH of 3 aren't one different from each other. They're 10 levels, like 10. It's a whole order of 10, okay? So a pH of 7 has 10 to the negative 7th molarity of hydrogen ions, or 0.000001 molar hydrogen ions. You don't need to know these numbers. You need to understand this relationship. 10 to the negative 5th isn't like 2 times more acidic, okay? 10 to the negative 5th is 100 times more acidic, because it's 2 orders of 10. It's 10 times 10, right? You guys know how logs work, right? It looks like this. It's not a straight line like that. It increases logarithmically, okay? So 10 to the negative 9th would be 100 times less acidic, right? Because the closer you get to 1, the more acidic it is. The closer you get to 14, the more basic it is. Does that make sense? Let's do this was the clicker question from class, so I wanted to go over it again in case people were like, I didn't understand that. A pH of 3 has 1,000 times more hydrogen than a pH of 6, right? Because as you get closer to 1, it's more acidic, and it's 6 minus 3 is 3 orders of magnitude more acidic, so it's 10 times 3, it is 1,000 times more acidic. Huh? 10 to the third. You guys, this is why I'm not like some kind of math SI. I keep screwing these up. It's not 10 times 3. It's 10 to the third. Okay?
When the H plus increases or decreases, does the OH negative do the opposite?
Yes.
Do we need to know like different things at the different levels of pH, or will it just ask things like that?
How do you mean?
Like bleach is more.
No. I think he showed like a scale that like oven cleaner was here and battery acid was here and stuff. You don't have to have that memorized. It was just to kind of show you.
What was the word for the chemical that increases as the hydrogen ion increases?
Are you talking about hydroxide?
Yep, that's the one.
Yeah. So technically you can also measure the basicity, I think that's the word, the basicity of a chemical, of an element, of a mixture by looking at the hydroxide, because again, as hydrogen goes up, hydroxide goes down, and opposite of each other, right? But we just look at pH, right? Is the measure of hydrogen. But yeah. All right, so let's practice that again. A little bit of mental math here. You should be able to do this pretty much in your head or a little bit on paper, but you shouldn't need a calculator. A solution with a pH of 11 has blank times blank concentration of hydrogen than a solution with a pH of 3. I'll give you like 45 seconds. Not even 45 seconds because we're in a hurry. Who thinks it's A? Who thinks it's B? Who thinks it's C? Who thinks it's D? Pretty much all of you said B because you're cheating by downloading my slides. No. So who wants to explain to me how they did this?
I took the pH of 11 and subtracted it by 3. And then you get 8. So then you know it's 10 to the 8. And so then just like kind of looking at it and knowing the scale, at least in my head, I was able to understand that it was less.
Yeah. So again, the higher the number, the less acidic. So 11 is far less acidic than 3, right? Does everybody see how that happened? Does anybody want me to explain it again or explain it in a different way? Do you feel like you could answer a test? Raise your hand if you feel like you could answer a test question about pH similar to this. Okay, that is good enough for me. So this is what I was talking about when I said don't worry about it. I'm careful to say don't look at it at all. You should look at it and you should know those names and things like that. Do not freak out about it, okay? I freaked out about it. I sat there and I drew it out a million times and I tried to memorize it. Guys, I'm in organic chemistry right now. I still don't have these memorized, okay? Which I probably should. Don't tell anyone. You're not going to need to like memorize every single little detail here, okay? Just kind of be familiar with, if you heard the word methane, you would go, yeah, that's a molecule. I don't know what it looks like. I don't know what it does, but I heard it in biology, and I know that it's a molecule, okay? Same thing, ethane and ethene, but don't freak out. And then these are all the groups. Know the names, okay? So if you hear amino group, go, oh yeah, that's a group on a molecule that I've heard of. I don't know what it is, I don't know what it does, I don't even necessarily know what it looks like, but I know that amino groups are part of a molecule. Okay? That is it. Any questions? Did the roll get all the way around? I hope. Who has the roll? Back there. If you didn't get the roll, come up to me and just sign it real quick up here. I promise I won't go this long every time. We just had a lot of stuff. Sorry. Thanks for coming. Enjoy the rest of your day and your lives. Do great things. Be great people.